Hello, everyone, and I am back. And this lesson, I'm still talking about area between two curves, but I'm actually showing you multiple methods we can use now, because what you learned was one way you can do this, but there isn't just that one way. Sometimes other ways are more effective. So we're going to do it all through this problem here, where calculate the area enclosed by the regions below, where we have f of x is x squared, g of x is 6, and h of x is negative 3x plus 6. So if I make a sketch of this to help you visualize this, we have the function g of x, which is just a constant, at 6, x squared, which is a parabola that'll look something like this, and negative 3x plus 6, 1, 2, 3 over 1, 1 will look something like this, and there's h of x. So what I want to know is the area of this region here. Now, previously, from my last video or from the lessons we've done, one way we can find, so approach one method we can do to get the area of these curves is calculate the integral using, so we're going to use the integral, the area between curves, but we're going to use vertical rectangles. You might be saying vertical, and I don't even know what you're saying. Don't worry, you've done this before. So if we were to calculate the area using vertical rectangles, an example of one being here, one rectangle, where the width of that rectangle, so if I bring this out here, the width is going to be changing with respect to x. So change of x, or what we'll be referring to it as dx in the interval. And the length of this rectangle, or the length or the height, will be the function g of x minus, because that's the upper function, minus its lower function, which is h of x. But notice if we kept doing these vertical rectangles, and infinitely many of them, is we have g of x minus h of x. These rectangles will be fine until we get to this intersection point here between h of x and f of x, where it'll no longer be, we look at a rectangle now on this side that I'm going to try to draw. Well, that rectangle now is going to have a height of g of x minus f of x. So the height is going to be calculated using a different set of functions. We can't just use the same set of functions for all of it because it changes once you get to that intersection point. So if we do it with approach one, we're going to find infinitely many rectangles here. And again, we can write infinitely many rectangles with the integral. It'll be the integral from, so we know that this is the point 0, 6. We need to find this intersection point here. So I'm just going to use our calculator here rather than do it by hand. So I've already put these into my graphing calculator. If we graph this, here we have it. And let's calculate the intersection point at this location here. Guess there. So that intersection point is 1.3722813. On this side so I can write this down. And if you remember what I was saying, you don't want to do 3 decimals during the problem. You want to do at least 5. So let's do 2, 2, 8, 1, 2, 3, 4, 5. And then the y value would be 1.88316 approximately. And then the second intersection value, well, that's at 6, comma, and I know we can do it by hand, but I'm just going to stick with the calculator here. Guess at that point, that intersection point is 6, 2, or sorry, 6. The x value is not 6 there, because it has to go right first. 2.44949, 6. Okay. So those are our intersection values. So if we want to find the area here, it's going to be from 0 up until 1.37228 of the top function, the upper function g of x, minus its lower function, which is h of x, with respect to the changes of x. Those are the widths of the rectangle. And then we have to add on the second area there, which will go from 1.37228 to 2.44949 of the upper function minus the lower function there, which is f of x with respect to x. Okay, and now we want to put this in our calculator, have it calculate for us. So this is what's going in my calculator again. And again, I like to write it out so I know how many parentheses to use. G of x is 6, so it's 6 minus negative 3x plus 6 plus this integral 449. I was making sure I wrote that right with all the 4s and 9s. I said, dang, 6 minus x squared. I don't need that. And what we'll get using this method, now let's see what we get. So, math 9, 0 up to 1.37228 of 6 minus, I'm going to use parentheses for this next function, dx. And I'm going to put this all in 1 so I don't even round later. So then plus the integral from 1.37228 up until 2.44949. And this time it's of 6 minus x squared with respect to x. And all of that, this area is approximately 5.250 units. And again, the book says units squared. I don't necessarily like that, but that's okay. And that's the area using one method. And that's not bad. It's really not too difficult. But is there an easier way? Say you're wanting to program this because there's a lot more graphs going on. And with programming and computer science and with anything in the world, we always are looking for the most efficient method. So what is a different approach we can take? A different approach we can take here is if we're approximating this region here, instead of looking at vertical rectangles, we can actually find the integral, the area under the curve, using horizontal rectangles. We don't have to make vertical rectangles. No one ever said in the rules of integration, nowhere did I say, hey, vertical rectangles only. That's not true. Notice if I do horizontal rectangles, so I take a snippet of one right here, right? And that's, obviously that has a bigger width than we would like. We're going to be taking infinitely many horizontal rectangles. Well, if we take infinitely many horizontal rectangles, they're going to fill up this space from the bottom to the top. So notice if we do this method, infinitely many rectangles with horizontal rectangles, we're now evaluating with, well, let's do it down here. So if we look at a horizontal rectangle, bring it out down here, zoom out just a tad. Right? Let's figure out the width and height as that'll help us write the integral, because the integral is just infinitely many of these rectangles. Well, this length here is now just the rightmost function, which is f of x, minus the inner function here, the left function, which is h of x. So to help you see this is, if I took the integral of f of x out here, well, I'm going to calculate everything from the curve up until the y-axis now. So that, if I had a picture of this, recreate it something like down here. So when I do the function of f of x, say it's from here to here, I'm finding this entire area to the y-axis now, not to the x-axis anymore. And then I'm subtracting off h of x, which is the area from the leftmost curve over. And by doing that, this height, that height of that rectangle, this height right there, Well, notice that that is f of x minus h of x, where this curve again is h of x. So if we're writing the integral of this, and notice that that stays the same throughout. We don't have to consider it jumping at a certain point like we had to do here of writing two integrals. So we know it's going to be f of x minus h of x. Oh, I'm sorry. And it's not really of x. Notice how these are changing vertically. It's changing now with respect to y. The width of these rectangles as they get infinitely smaller are going to be a change of y, dy. So then we don't actually write f of x minus h of x. It's actually f of y minus h of y, because now we're talking in terms of y. Man, I'm saying y a lot. I'm sorry. So it's h of y, f of y minus h of y as we change with respect to y these infinitely many rectangles in this space here. And then our integral is going to go from our bottommost point, but remember we're looking with respect to y, so when we look at this intersection point, it's not the 1.37228. We're looking at from 1.88316 up until the top here, which is at 6. And that will give us, hopefully, crossing my fingers, but not really because I know it will work out, will give us the same area as this. Now, hopefully you're with me still. So we're doing horizontal rectangles with respect to y as these change up vertically. And it's going to go from a lowest point of 1.88316 up until 6. If you want to make notes to yourself, you might want to say that that's the right function. So we used to say upper function and lower function. Well, now we're doing the right minus the left function. Okay. And what we'll get here is, well, I'm wondering to myself, is it always right minus left? Like if this graph were to be on the left side here, would we still do right minus left, or would we do left minus right? I believe it wouldn't matter. No, I think you might have to do, yeah, I think you'd have to do left minus right if you're on the opposite side here, because when you find the area in the curve, it's with respect to the y-axis. So, side note, something I just discovered is that this is true because we're in the positive x values. If we were in the negative x values, these would actually get switched. It'd be left minus right. Just like I believe if we were doing an area function below, well, you can actually do top minus bottom. It'll fix itself in the end with two negatives making a positive, so that won't matter. So it actually doesn't matter here. You can do right minus left, so it would fix itself in the end. Okay. So, side note, sorry about that. So when we do f of y minus h y with respect to y, notice this we don't know what the function is, so we actually have to find these functions now. Well, f of y, well, f of x was x squared. So if we write that as y equals x squared, we have to write this in terms of our inverse y. So that's where you switch and find the inverse, where you switch x and y and solve for y, square root both sides. So we get here that y is the square root of x. Or if we're keeping this in terms of y, we could have just written this, instead of changing the variable x and y, just solve for x and get the x as the square root of y. So let's actually write that instead, because that's not true. F of y should be the square root of y, because you're taking inputs y. Right, so disregard that. And then h of y, let's see here, h of x was negative 3x plus 6. So if we solve for 6, we'll get here the x is equal to y minus 6 over negative 3. So h of y will be y minus 6 over negative 3. So now let's put this in our integral here and finish this out really quick. Up to 6 of f of y, which is root y, minus h of y, which is y minus 6 over negative 3. And all of this is with respect to y. And hopefully, we get 5.250 approximately. Let's find out. All right, math 9, 1.88316 up until 6 of, now how do you put y? Now a calculator doesn't know variables. All it knows is that it's doing it with respect to these variables here. It won't matter. A calculator or y and x mean the same thing to it, so don't worry about that. Square root of x minus, follow my parentheses, and I'm going to put another parentheses here because on a calculator I want to make sure it recognizes the numerator there. So another parentheses of x minus 6 numerator divided by -3, close parentheses. Then you have the other parentheses, and then the x, which will represent the y here. And do we get the same thing? Notice that we do. And I know I'm approximating to just 5.250, but you can see even farther out, those are the same thing. And again, just understand that these units, not necessarily units squared. So there is 2 different ways. And are there more ways? Probably, but these are the most common, where we can either get the area between 2 curves. Fix my focus really quick before I do my summary. Is you can either find the area using vertical rectangles, which are respect to x, because that's changing left and right, or you can use horizontal rectangles, which will be with respect to y. So 2 different ways to think about it. Just be careful that if you do approach 2, you get the functions in terms of y. That's a mistake that most people make. Okay. Well, there you have it. Hope that clears it up. Hope you didn't get too disturbed by my sidetrack of, does this work for the other side? And I believe it does. You're more than happy to check it out. There's math. We have questions and we want to know if they work, and we have to check them out. Hope that helps. Let me know if you have any questions. All right. Bye-bye.